Hey everybody, it's Dr. P with this week's frequently asked questions for, I believe this is week 2 now. I got a couple of questions, actually I got a lot of questions on how to graph equations in 3 variables. That was by far the most popular topic this week. I've selected a couple of specific questions for us to focus on in this video. One of you asked, is there a specific time when contours or cross-sections should be used? And then another one of you asked, or said, I need to work on cross-sections, what they are, and how to put them together to view a 3D object. That last comment there actually hints at what I consider a secret technique that is very handy when graphing equations in 3 dimensions. We're going to try doing that in just a minute here, but first I want to address the question about when you should use contours and when you should use cross-sections, because that's a strategic choice. It's usually not something that you'll be directed one way or the other. I've put up an equation for a function f of xy equals y squared times e to the minus x. And we're going to try analyzing this from a couple of different points of view. Okay, so the question was, when do I use cross-sections and when do I use contours? Remember, a contour is a cross-section of a graph where you're setting z, or in this case, the function value equal to a specific constant. Let's try doing that here and see what happens, shall we? Let's try setting f equal to some nice innocent constant like 1. And look at the contour that we get. So we get z equals 1. We get the equation 1 equals y squared e to the minus x. And I can rearrange that equation and get y squared equals e to the x. Now at this point I could do more work. I could, for example, take the square root of each side and get y equals plus or minus e to the x. Notice that I need the plus or minus because in this equation here, it's not necessary that y be positive. It could be negative. I could even go a step further and say that y equals plus or minus e to the x over 2 if I were clever. Okay, and I could try graphing that. That wouldn't be a problem. But keep in mind, I've only done that for the number 1. It's going to look different depending on what that constant is. That doesn't look like the thing I want to do first. I mean, this is not too bad, but there are simpler things that I can do here, and I'm going to try doing those before I proceed with this. In some cases, you'll try writing down the algebra for a contour and discover that there simply isn't a nice way to graph the equation that you get. I mean, even when we did this one, it took quite a bit of cleverness for us to get to the point where we could think about graphing. We can come back to that in just a bit if you want. But for now, I'm going to try doing something a bit different. I'm going to try looking at cross-sections rather than contours. So let's try cross-sections parallel to the xz plane. Okay, so when I want cross-sections parallel to the xz plane, that's like this plane here. If you look at the xyz space in its standard orientation, so what that means is that we're fixing a certain value of y. So for a fixed value of y, let's call that a constant c. This equation turns into f of x comma c equals c squared e to the minus x. All right? Now, another way of saying this that's a little less fancy is c equals c squared e to the minus x, keeping in mind that c is the value of y. Now, the key thing to notice here is that this is a constant, and what I have here is a decaying exponential as x increases. If c is very large, that exponential is going to start at a large value. If c is 0, this thing's actually going to be completely flat. If c is 0, then z equals 0 whenever y is equal to 0. In fact, since I know that when c is 0, z is equal to 0, since I know that, I already know one curve, or one line actually, that's going to appear in my graph. It's going to be this line. So whenever y is 0, my z is 0. That means this graph is flat along the positive x-axis, and actually along the negative x-axis as well. So that line is part of my graph. Okay, now what if c is something else like 1? So what if y is 1? If y is 1, then I have z equals 1 squared times e to the minus x. So if y is 1, then I'm going to start at 1, and my height is going to decay as I move in the positive x direction. And similarly, if y is negative 1, then again I get z equals negative 1 squared, or 1, times e to the minus x. So this equation is true when y equals 1. It's also true when y equals negative 1. I get z equals e to the negative x again. So over here, where y is equal to negative 1, I'm going to put a point at height 1. Notice that it appears to be a different height because I've got the y-axis oriented a bit differently this time. And I'm going to have a decaying exponential once again. Okay? Notice these are flattening out as they go this way. It's hard to tell from the picture, so you have to use your algebra sense even as I'm drawing. Okay, now what if y equals 2? If y equals 2, then this equation becomes z equals 2 squared, or 4, e to the minus x. Now I have a higher initial value, much higher, but again, as I move in this direction, in the plus x direction, z decays quickly. And over here, when y equals negative 2, I get the very same thing. Okay? So it's like I have all these decaying exponentials that are starting at different heights, but as x increases, they all sort of flatten out. So what I'm going to get is a surface that's composed of a lot of these exponential curves. Okay, that's one perspective. Now, if I want another perspective, I should try fixing something else. Rather than fixing y, I should try fixing x. Now I'm getting cross-sections parallel to the yz plane. Okay, so what happens if I fix x? If x is equal to 0, then I get z equals y squared times e to the minus 0, which is just y squared, because after all, e to the 0 is 1. Okay, so I get z equals y squared. I know what that's going to look like. It's going to look like a parabola. And if you've been paying attention, you'll notice that I actually have the beginnings of that parabola here already. So when x is equal to 0, I have the parabola z equals y squared. It's going to look a little bit odd over here. No, it's not too bad. And now we're starting to get some real clues about how this surface fits together. Okay, I tried plotting all those exponentials, but it was a bit hard, even at that time, to see how they would all fit together in order to form a three-dimensional surface, a two-dimensional surface sitting in 3D. But now I have an idea of how they might fit together. They're going to fit together in sort of a parabolic fashion. Now, what if x is equal to 1? If x is equal to 1, then I get z equals y squared times e to the minus 1. E to the minus 1, I don't know exactly what that is. It's going to be something like 0.3 something. It's some smallish number. It's some smallish constant times y squared, which means, again, I'm getting a parabola, but this time it's a little bit flatter because I've multiplied by a constant that's less than 1. So when x is 1, I get another parabola, this time one that is a bit flatter. Sorry, that should go through x equals 1. Okay. Okay, so another parabola. I've just drawn the beginnings of it here, and it's a lot flatter than this first one. If I increase x some more, you can probably figure what's going to happen. This is going to become an e to the minus 2, an even smaller number, and flatten that parabola out even more to the point where it looks almost like a horizontal line. It might look like that. So now I have at least a partial picture of this surface, and it's not too bad. It might help if I draw more cross hashes here. More here. And maybe more contours in the other direction. And at this point, it's really more of an art project than a math project. And I think you get to the point where it's like that with your graphs as well at some point. But what I have is a surface. I don't know if there's a special name for this, but I think I could model it if I had a sheet of paper around. It's like if I took this sheet here, left it flat over here, and then took the corners and did this. Now, it's hard to do this without a second set of hands, but I'm trying to take these corners and pull them up while leaving the other end flat. And it's hard to do with just two hands, but I think you can kind of get the idea. I'm pulling these two corners up, but leaving the other end of the paper flat. That's the sort of surface that I'm getting. And we were able to find that by not just finding haphazard cross-sections, but by finding cross-sections in a very systematic way and then thinking about how they progress as I increase x or increase y, increase whatever the variable that I'm fixing is. Okay? That's really, to me, the difference between students who do this skillfully and students who struggle with this a lot, is not only can you find, if you're a student who's successful at this, not only can you find a cross-section for a fixed value of x, but you can think about how that fixed value of x, whatever it is, changes the graph. So in this case, you'll notice we said, as I increase x, it's still a parabola that I get here, but that parabola gets flatter as x increases, okay? So I have a parabola that starts like this. Okay, this is when x equals 0. And as I move in the positive x direction, which is going to be towards you, this parabola is going to go like this. And it's going to flatten out. If you can think about that progression, you're going to have a lot more success with these graphing tasks. Okay, so that's one. But I did want to say one more word about what happens with those contours, because I sort of skidded over that issue when I went over it the first time. So what about the contours? We said earlier that a contour can be gotten by setting f equal to a specific value, so let's call that c. And then after doing some algebra, I get y squared equals e to the x, and y equals plus or minus e to the x over 2. Where are those curves in the graph? Well, contours are curves that are at constant height in my graph. If I look at this picture here, I notice, and it's hard to see from the cross-hatching is a little bit deceptive in this regard, but if I start here, this is at some height, and you'll notice that as I move towards the y-axis, I have to move towards the inside of the shape in order to stay at the same height, because this is actually quite low compared to these corners here. Okay, so if I want to stay at the same height, I'm going to have to move sort of like this. And then I have another curve at the same height here. Okay, this is not a perfect picture here, but you'll notice that there are two curves at the same height. Those are your plus and minus, and then e to the x over 2, that's an exponential that's growing at some rate. I don't think I've gotten the curvature exactly right in this picture, and it's really quite hard to do. But if you use a program like Mathematica or Maple, you can actually see those in your picture. There's a way to highlight those. Anyway, that's the first video. My next video will be about how to tell some common shapes apart.